So, once you know the heat, obviously you also know how you transfer from one place to other place, is not it? So, that means that the heat is generated in an arc and that heat will be transferred by maximum 3 ways. That is what nature says, is not it? By conduction, convection, radiation. In a normal conductor, how the heat is transferred? You have one rod, okay? You apply some heat in this end, then heat is transferred, right? Assuming that there is no radiation heat transfer or convective heat transfer. So, mainly by a pure conduction. So, how does heat transfer from this to this place to this place? By vibrations. What happens during vibration? So, when they vibrate, they collide. During this process, it is transferred from one place to other place. So, that is a classical heat transfer by conduction. Okay? And we can estimate the heat transfer by calculating the temperature difference between these two ends, isn't it? So, the change in the heat delta Q from this end to this end is nothing but, if you measure the temperature and the length, you can calculate how much heat is transferred from this end to this end, isn't it? It is a classical conduction heat transfer equation, isn't it? So, if you know the temperature gradient of an unit length, you can also calculate how much heat is transferred from this end to other end. In other words, the amount of heat transferred by conduction is directly proportional to temperature gradient, isn't it? The proportionality constant is K. K is, what is that K? It is a heat transfer coefficient, whereas in arc a lot of other things can also happen, isn't it? So, the K, the heat transfer coefficient, right, can happen by 4 ways again. The first one is classical way, by collision of heavy particles, by collision of atoms, gas molecules. Okay? That means that if a one particle which is hot is collided with the other one, obviously heat is transferred from one place to other place. So, that is a classical heat transfer coefficient case. It happens in conductor, for example, in a copper rod. Okay? But in arc, we also have the ions, the electrons. We are also continuously ionizing the gas, and we are also dissociating the, if you have the diatomic gas or molecular gas. So, in all 4 ways what I listed here, the heat can be conducted in an arc. The first case is classical heat transfer coefficient by collision of heavy particles, atoms and gas. In second case, when the electrons collide with the heavy particles, isn't it? That is also possible. Hot electron, it goes somewhere and then collide, obviously it transfer heat from this point to this point, isn't it? So, that is, we can term it as Ke. The first term, the classical heat transfer, is Kg, if you assume. And 2 other phenomena is also possible because of the ionization. Imagine there is an argon atom here in the inside the arc, it ionizes, okay? And the ionized argon atom, argon plus, goes over here. It is attracted by an electron diffuse again back to this argon plus, it becomes argon atom, and that is an exothermic process, because electron gain is an exothermic process, isn't it? Ionization is endothermic. Similarly, here the argon plus is in different temperature. If it goes over there, it also carries heat with it, whether it is a positive heat or negative heat, does not matter. Heat is transferred, plus you also have a deionization, isn't it? That can also happen. So, ionization, the ionized gas atom can also be deionized, and during this process the heat is transferred, whether it is negative heat or positive heat does not matter, but there is a heat transfer, isn't it? So, that is also possible in one way of transferring heat from one place to other place, whether you are making the other place hotter or this place become colder does not matter, anyway the heat is transferred. In this case here, when you are doing ionization, heat is absorbed, isn't it? In a way this absorbed heat is released elsewhere, isn't it? So, you have an ionization process, that is endothermic, the ionization energy is observed in this point, that means that you are packing an energy in this point, sending it back to other point. In this point that energy is released, something like you have a lunch box, you pack it and then eat it there to gain energy. Okay. So, the ionization energy which is consumed for ionization is released elsewhere by the deionization. It is a heat transfer, isn't it? So, that can also happen. Similarly, the same thing can also happen for dissociation. You have a nitrogen N2 becomes 2 Ns, they can also go and combine becomes N2 again. Same as ionization and deionization, you can also have dissociation and de-dissociation, isn't it? So, these all 4 heat transfer by conduction is possible in arc, and this is extremely important, especially if you are using a diatomic gas, and this can be very significant, okay, because you always continuously dissociating and de-dissociating, and that can influence the arc temperature along the radius of an arc, along the length of the arc. Okay. So, the total K of an arc is nothing but Kg, that is the classical heat transfer coefficient by the collision of heavy particles, atoms and molecules, and then the collision of electrons and heavy particles. The electrons carry the huge amount of heat, they also have a much higher drift velocity, and they determine the electric current in an arc, we just saw, isn't it? And then the diffusion of ionized pairs, an ionized gas atom combines with an electron becomes a neutral gas atom. During this process it liberates whatever it consumed during the ionization process. Okay. The same thing can also happen with the dissociation and de-dissociation. So, by conduction in an arc, heat is transferred by all these 4 mechanisms. In a classical solid conductor, these go away, you have only Kg, but in arc unfortunately we will have to account for all these 4. So, when you look at how heat is conducted in an arc, so we need to calculate all these 4, and these 4 reactions would determine the temperature distribution if you neglect the radiation and convection heat transfer. So, these 4 would determine the arc temperature. Okay. How? Like this. So, this is the total coefficient, heat transfer coefficient by conduction. So, Kd, what is D term? Dissociation, de-dissociation, that can be significant at lower temperatures. Okay. At higher temperature you have deionization. Okay. Ke is the collision of electron with heavy particles, and then Kg is the classical heat transfer, okay, by the collision of atoms and molecules. If you sum it up, this is how the distribution looks like. If you use a monatomic gas, then this shoulder goes away, isn't it? So, if you mix your arcing gas with diatomic gas, it would considerably change the temperature distribution of an arc. Okay. So, if you use a diatomic gas, 100% diatomic gas, the heat distribution by conduction in an arc will be entirely different than if you use monatomic gas, right? It's clear? Good. So, this works, I mean, in real case as well. For example, this is a temperature profile of an arc neglecting radiation convective heat transfer. So, we have calculated temperature profile of a plasma with diatomic nitrogen and a monatomic nitrogen gas. And what you see over here, it is R by R0. R0 is the radius of an arc at any given location. If it is center, that means it becomes 0, right? R becomes 0. At the center, you have the center of the arc. If you look at the temperature distribution, the solid line is for diatomic gas. You see the two shoulders, there is one change in slope and another change in slope, and this is corresponding to Ki and this is Kd. K is, what is Ki? Deionization, okay, and this is Kd, which is dissociation. And if you use a monatomic nitrogen, obviously the Kd completely goes away, isn't it? The temperature distribution is more or less a parabolic, right? Is it clear? So, obviously from this graph you can clearly say that instead of using monatomic nitrogen, if you use diatomic nitrogen, the arc temperature will be much lower at a given location. So, for example, at the center of the arc, okay, or halfway from the center, the temperature of an monatomic nitrogen will be somewhere of 9000, whereas in a diatomic gas it will be much lower, yes, about 6000 Kelvin. So, we often see mixing of diatomic gas as a shielding arcing gas to control the heat in the arc. Okay. Similarly, if you use diatomic gas, heat is also effectively transferred. It is not only concentrating at the middle, isn't it? Because the de-dissociation can effectively transfer the heat from the center to elsewhere. That is what it shows here, isn't it? It not only reduces the temperature of an arc, it also effectively conducts the heat from one place to other place. So, that means that if you want to reduce the penetration and if you want to make the well bead wider, so obviously you can use diatomic gas, isn't it? Because heat is distributed much widely, whereas if you use monatomic argon or helium, you have a deeper penetration, but a narrow well pull. Yes, it's clear. We will see in the case studies how this effect is going to affect the real life. So, now you need to understand that if you use a diatomic gas, the heat conduction will be much more efficient than using a monatomic gas, because of the de-dissociation can effectively transfer the heat from the center to elsewhere, and during this process, okay, so the temperature decreases, okay, because the dissociation also effectively absorb the heat. Yes, it's clear? Example? Good. So the second heat transfer, which is also very significant in terms of arc. Heat transfer by radiation. Have you seen an arc? What is the color? Color of an arc. Don't stare an arc by naked eye, isn't it? So look at the spread. This is the spectrum of an arc. You see the peaks, where are they appearing? Between 400 to 500. So what is the range? 400 to 500. The entire range is up to this is visible, right? So that's a blue range, isn't it? So that's a blue spectrum. So the maximum intensity is liberated in the wavelengths of about 400 to 500 nanometers. Okay, that's the same. All your shirt colors, black, it's absorbed, black body. So no radiation is emitted, no wavelength is coming out. Yellow, isn't it? Why the shirt is yellow? The intensity, the maximum in the yellow range, isn't it? So you have two color t-shirts. Okay, so I have the peaks are two different wavelengths. That's why your t-shirt looks two colors. Okay, the same with the arc as well. So arc, we assume that at temperature is because so high, it's a continuous radiation, like a black body. Okay, it's not a line spectrum. It can be line spectrum only at very low temperatures. Because of the temperature we are talking about is 20,000 Kelvin. So we can safely assume that it is a continuous spectrum. Okay. So with the peaks between 400 to 500. So that's how when we are recording the arc, we always use band pass filters. You know what are the band pass filters? No? So if you record with the camera, normal camera, arc, you won't see anything because the wavelength is so spread, you will just see only one glare. Okay. Suppose if I want to study how the electrode is melting, I don't want to see the arc, isn't it? I want to see only the electrode part. So what we do, I will use a band pass filter. So band pass filters, they filter all the wavelengths except one tiny range. Okay. Suppose if I use a 690 nanometer band pass filter, okay, this band pass filter will allow only the wavelength coming from 690 nanometer. That means that I would mask the entire arc. So I can look at only the well pool, for example, isn't it? Otherwise the arc is so bright I won't see anything, isn't it? Or if I want to see only arc, I don't want to see anything else, I can choose a band pass filter between say 400 to 450. That means that the lights coming from this region would only reach my camera. Okay. So I can look at only arc, nothing else, isn't it? So the color of the arc is bluish white because it has all the wavelengths, therefore white, with some peaks in bluish range. You see the peaks in blue range, that is why we see arc as a bluish white. Okay. The same goes with all your shirts or eyes. See the colors, whatever wavelength is coming from your shirts. Okay. So by assuming a continuous radiation, not a line spectrum, if it is a continuous radiation, it is a black body, right? Then we can use one equation to calculate the heat transfer. What equation? Heat transfer by radiation. Yeah, Stephen Boltzmann equation. Okay, what is Stephen Boltzmann equation? Okay, so this sigma, Stephen Boltzmann constant. Shouldn't be confused with the other Boltzmann. So this is different. Okay, so this is Stephen Boltzmann constant. Okay. So here. So if you assume the arc is a continuous spectrum, has a black body. So once you assume that, obviously at higher temperature it is a continuous spectrum. If temperature is low, then only you get a line spectrum, then this equation is not valid. Okay. So plasma becomes continuous spectrum at higher temperatures. So this is a black body radiation. The assumption here is it should be continuous spectrum, which in a way we can assume at higher temperatures. So once you know that, we can calculate again heat transfer by radiation. It is significant compared to conduction, about 20-30% is by radiation. Okay. So when you are welding, you just take your hand close to the arc. Okay, you feel heat, right? So that's being radiation. Okay, so if Baba goes to IIT Guwahati, you will do for intra IIT, you will do a campfire, right? You will not transfer the heat by conduction, isn't it? So you make yourself warm by radiation in campfire, isn't it? Maybe convective flow as well, because air also brings that will next heat transfer. The majority is by radiative heat transfer. Right, it's clear? So we calculate the heat transfer by radiation by the Stephen Boltzmann law. So Boltzmann also did a lot of work, isn't it? Poor guy, I don't know why he committed suicide. I'm really feeling for him. So then the third heat transfer mechanism is convective flow. And this is also significant, how the heat is transferred from one place to other place in an arc. Okay. There are two ways the heat is transferred by convective heat transfer. So one is very simple, buoyancy flow. What is buoyancy flow again? Because of the density difference. Gases at high temperature will be less dense than the gases at low temperature, and that will lead to a buoyancy flow, isn't it? Due to the difference in temperatures, the gas will be in different density at various locations. Obviously, gas will flow from one place to other place by buoyancy because of the density difference. But that is slightly negligible compared to the other major force in arc, that is known as plasma jet. Okay. The plasma jet can be created with very high velocities. Okay. The principle is very simple. For example, so this is your electrode. Okay. Obviously, at this point, at the center of the arc, if this is your arc, you have an accumulation of charges, isn't it? Cathode fall zone or anode fall zone. Okay. So we can divide the entire transfer of current into very small particles, obviously either electrons or ions, isn't it? These are charge carriers. So these charge carriers, they have a peculiar property. For example, if they come together, obviously they will repel. Okay. So the force is inversely proportional to the distance, isn't it? If they are really close, they create enormous amount of force to repel. So obviously, if you have accumulation of charges in one point, obviously in arc you always have accumulation at the center of the arc, at the tip of the electrode, for example. So then you create a force what you call as Lorentz force. So Lorentz force is nothing but when the charge carriers, when they come close, they repel much faster. there is a force created in the fundamental the electric charge carriers. When they attract to each other, obviously they will be repelled much faster. So, the force at which repelled is inversely proportional to the distance. So, if you have accumulation of charge carriers, they will be repelled into enormous velocities, isn't it? So, that force is known as Lorentz force, and Lorentz force in arc is very significant. Okay. So, if they are accumulating, they will be repelled, isn't it? And this repulsion creates a jet, and that is known as a plasma jet. And this jet can go as fast as 200 meters per second, 200 meters per second. So, the flow inside the arc plasma can go as high as 200 meters per second, okay, at the center of the arc column, because of the accumulation of enormous amount of charge, okay, creates a Lorentz force leading to a jet formation. So, obviously, once you have jet, you have transfer heat, isn't it? So, you also have heat transfer by the flow, which is convective flow heat transfer. Yes guys, it is clear? So, if you look at plasma flow in a just simple 200 amperes arc in air. So, the center, so this is your electrode, the flow close to the electrode can go as high as 200 meters per second, and if you go far away in the arc envelope, at the envelope side you do not have the accumulation, isn't it, of the charges. Charge accumulation always happens either at the cathode or anode, and here you have accumulation is spread, okay, because obviously the base material, either it is anode or cathode, it will not be accumulating at one point, it will be spread, right. But here the tip is a very tiny area, right. So, then there is enormous amount of accumulation of these charge carriers, and once they accumulate, they will repel between each other, creating a jet force, and this jet force can also transfer heat, and that is one way of convective heat transfer. So, now, so we have three types of conductions: convection and then radiation. Conduction again in four types: heat transfer by classical heat transfer, by the collision of atoms and molecules, and then that is Kg, and then Ki, the collision of electrons with heavy atoms, heavy molecules, that is Ke, and then Ki, deionization, and then Kd, de-dissociation. That is the conduction heat transfer, how the heat is transferred in an arc. And then radiation heat transfer, it is Stefan-Boltzmann law by radiation. And then convective heat transfer, two types, by buoyancy flow, right, and then by plasma jet formation due to the Lorentz force creation. Okay, the charge carriers, the repel when they are placed together, creating a jet force. Okay, so now we generated heat and we transferred the heat. Now we can weld, isn't it, right? So, we will look at the various welding processes, and when we look at the welding process, then and there we will discuss about the physics, whatever we learned so far. Okay, so how the heat is generated, how heat is transferred, how efficient is the process, okay, and if you use one gas, how the efficiency can change, how heat generation can change. Okay, so we will move when we look at each process, we will use this basic to understand the physics of the process, right. It is clear? Good. So, I am showing you a very simple schematic of a typical weld setup. So, now we are moving on to the actual welding setups, welding processes. So, what is he over here? So, obviously you need to give E, isn't it, and then you need to generate electrons. So, for that you need a cathode, and then you need an anode to receive whatever you generate, is not it? During this process you also need to have a gas which can be ionized, so that you can strike an arc, and once you struck an arc, the process itself, the ionization, would determine the heat generation by the term JE, is not it? And then from JE you generate heat, the heat is transferred by conduction, convection, radiation. So, this is the physics of the welding, arc welding, right. So, once you understand these concepts, now you can create your own process methodologies, because the fundamentals are the same, only thing is how you change these process variations. For example, here I have plotted in a schematic showing an consumable welding process. So, you have a power source, so that should generate E, okay, and then you need to have a cathode, it can be either this or it can also be minus, depending on your polarity. Okay. So, you need to have a gas for arcing, and then once you have arcing, obviously either you can melt the consumable, you can deposit, right. So, in the arc heat is transferred to the cathode and anode by conduction, convection, radiation, and inside the arc also heat is transferred by this way and you generate heat. So, by controlling E we can also control JE, and then NE can be controlled by the nature of the gas you use, is not it? That determines your ionization energy. Okay. So, once you know all these things, now you can understand the beauty of this process. Okay. So, it is a simple welding, you can see in the roadside, but if you look at the physics behind this process, it is an as good as an rocket science, is not it? So, once you understand all these fundamentals, you can enjoy the beauty of the process, is not it? So, we look at one by one. The first process, in a typical characteristics welding, you can either make the electrode consumable or non consumable. Okay. So, generally the distance between the tip of the electrode to workpiece not more than 10 mm, otherwise your arc stability decreases significantly, because then the conduction, convection, radiation, it becomes extremely unpredictable, okay, because the current density is distributed much over distances. Okay. So, it is not more than 10 mm when you want to strike an arc. Okay. So, either you can use a DC direct current, then you need to check your polarity. You want to make electrode positive or negative. What do you use if you want to use a consumable electrode? The electrons would reach electrode. Yeah. Then what polarity then? Yeah. So, electrode positive if you use DC. Okay. Or you can use AC, alternating current as well. Okay. That is also possible. So, now if you want to weld it, now obviously you can also weld it without a consumable, that is known as autogenous weld. So, welding without consumable. Okay. Or you can also use a consumable to fill the weld cavity. So, then in consumable welding process. Okay. So, you can use it with the various number of passes. Okay. If you appreciate the beauty of the physics, then you can also talk about the field. Okay. So, the voltage. So, again that is also important, like voltage in a welding process is a derived quantity, is not it? So, what we calculate here, E, that is the field strength. So, that is the current. Okay. So, voltage is a derived quantity. So, when you want to control the process, you always change the current. Okay. So, voltage is a byproduct. So that is why when you are saying that I welded, you never say I welded in so and so voltage, you always say so and so current. Okay. So the field strength determines your JE. Okay. So it's always we say that, so the welding is carried out in 200 amperes, we never say 10 volts, it is meaningless because voltage is a derived quantity, we derive voltage from R. Okay. So the current is rate controlling. So when you say that the current is important, so 100 amperes, I welded with 100 amperes or 120 amperes. Okay, the voltage is relevant, is irrelevant. Yes, it's clear. So you always use some E, the field strength, to generate JE, and that will determine your heat generation. Yes, it's clear. Good. So we will look at the types of welding processes and we will go one by one. And arc, using arc, we can see the various types of processes. And if you understand the physics, you can also create a new process or invent a new process, isn't it? So now you know the physics of arc. So basically you can modify the various parameters and you can also play around inventing a new process. So there are types of arc welding process we look at in this section: gas junction arc welding, gas metal arc welding. When does arc become plasma? When arc becomes electrically neutral. Okay. So there is a type of welding process, it's plasma welding, it's not arc welding. So we convert arc into plasma. Okay. So the plasma arc welding, and the shielded metal arc welding, submerged arc welding, flux core arc welding, electroslag arc welding, stud arc, and the new process magnetically impelled arc butt welding. We look at one by one. So this we are going to install in a couple of months in our lab. So these all welding processes, the majority of them are used in various engineering applications. So if you are employed in a construction company, okay, and you will be using one of the welding processes, okay, or if you are employed in any of the manufacturing, metallurgical, and if you are a metallurgist, obviously you should know something about welding, because that is the major manufacturing process. So you would be handling at any point of your life any one of these welding processes. So we look at, again, from the physics we understood how this process work. Okay, so how heat is generated, how efficient this process, whether all the heat you generate in the arc is transferred, okay, if not why, and can we quantify that. Okay, so that is what we are going to study. Okay, good. We will wind up here and then we will see next class.